Welcome to the lecture on inventory theory module 3. In the previous module, that is in module 1 and module 2, we have developed UQ models for single item only. Here in this module, we will develop UQ model for multiple items under restrictions. It should be noted that when we consider multiple items and develop inventory models, then we should not able to consider each item separately, because there exists some relationship among the items when we consider some restrictions. So, in this case we will first develop UQ model without considering the constraint. So, if we find the solutions which satisfy the constraint, then we get the optimal solutions. Otherwise, we will consider the Lagrange multiplier technique to solve the problem. Let us now start our discussion on model 4, which is multi-item inventory model without restrictions. The assumptions of the model are as follows. There are n items in inventory and lead time is 0 for each item. The cycle length of each item is the same for all items. Ri is the uniform demand rate for the ith item. C1i is the holding cost per unit of ith item per unit time. The shortages are not allowed in inventory. We consider C3i as the ordering cost per order for the ith item, and Qi is the lot size of the ith item in each cycle. The cost per unit time for the ith item can be written as Ci Qi equal to half C1i Qi plus C3i Ri Qi. The first term denotes the holding cost and the second term denotes the ordering cost. Hence, summing up this cost for I equal to 1 to up to n, we get the cost per unit time for all items as C equal to summation over I equal to 1 to up to n half C1i Qi plus C3i Ri by Qi. We have to determine the optimal values of Qi, that is the order quantities for I equal to 1 to up to n, so that the average cost C is minimum. The necessary conditions for optimum of C are del C del Qi equal to 0 for I equal to 1 to up to n, which give Qi equal to root over 2 C3i Ri by C1i, where I varies from 1 to up to n. It can be also shown that del 2 C del Qi 2 is greater than 0 for all Qi. This means that the average cost C is minimum for Qi star given in equation 3. Now, we proceed to consider the effect of limitation on investment, limitation on stocked units and limitation on warehouse floor space in each model. Now, we consider the limitation of investment. This is model 4a. Suppose that there are an upper limit, say m in rupees, on the amount to be invested on inventory. Let C4i be the unit price of the ith item. Then the total investment for n items would be equal to summation over I equal to 1 to up to n C4i Qi, and that investment should be less than equal to the budget m. Therefore, our problem is to minimize the average total cost, which is summation over I equal to 1 to up to n half C1i Qi plus C3i Ri by Qi, subject to the condition 4. Now, two cases arise. In case 1, if summation over I equal to 1 to up to n C 4 I q I star, where q I star is the optimal values of the order quantity, is this summation is less than equal to m, then q I star given in equation 3 can be regarded as the optimal values of q I. In the other case, if summation I equal to 1 to up to n C 4 I q I star is greater than m, then q I star obtained in equation 3 is not the required optimal value of q I. In this case, we will use Lagrange multiplier technique to find the optimal value of q I. The Lagrangian function L can be obtained as shown in the slide. L is equal to summation I equal to 1 to up to n half C 1 I q I plus C 3 I by q I plus lambda into summation I equal to 1 to up to n C 4 I q I minus m. Here lambda is the Lagrange multiplier. The necessary conditions for L to be minimum are del L del q I equal to 0 and del L del lambda equal to 0, which give q I star equal to root over 2 C 3 I R I by C 1 I plus 2 lambda C 4 I, where I varies from 1 to up to n, and summation I equal to 1 to up to n C 4 I q I star equal to m. Equation 6 indicates that q I star must satisfy the constraint 4 in equality sense, that is the constraint which is given in equation 4 is binding. Now, let us consider an example. We consider a shop which produces 3 items. The items are produced in lots. The demand rate for each item is constant and can be assumed to be deterministic. No backorder is to be allowed. The pertinent data for the items are shown in the following table. There are 3 items 1, 2, 3, and holding cost for the 3 items are 20, 20 and 20. Ordering cost for the 3 items are 50, 40 and 60, and cost per unit of the 3 items are 6, 7 and 5, and yearly demands are 10,000, 12,000, 7,500 respectively. We have to determine the economic order quantities when the total value of average inventory levels of 3 items is rupees 1,000. First, we compute the optimal value of the order quantity q I without considering the effect of limitation by using the basic formula, which is q I star equal to root over 2 C 3 I R I by C 1 I, where I varies from 1 to 3. So, using this formula, we can get the optimal order quantities q 1 star equal to 233, q 2 star equal to 216 and q 3 star equal to 210 approximately. But when we put these values in the constraint for the constant, we see that sigma C 4 I q I star by 2, which is the average inventory level at any time, we find that the sigma I equal to 1 to 3 C 4 I q I star by 2 is equal to rupees 1950, which is greater than 1,000. Hence, the optimal values which we have obtained without considering the restrictions are not exactly the optimal values. We now apply Lagrange multiplier technique and compute the optimal values q I star by using the formula q I star equal to root over 2 C 3 I R I divided by C 1 I plus lambda star into C 4 I, where I varies from 1 to 3. Here we have to find the suitable value of lambda, that is lambda star, so that summation I equal to 1 to 3 C 4 I q I star by 2 is exactly equal to 1,000. Now, we see that when lambda equal to 4, q1 star equal to 121, q2 star equal to 112 and q3 star equal to 123, and the cost of average inventory is rupees 1112.50, which is greater than rupees 1000. Again, if you take lambda equal to 5, then we obtain q1 star equal to 111, q2 star equal to 102, q3 star equal to 130, and the corresponding cost of average inventory is rupees 972.5, which is less than rupees 1000. This indicates that the most suitable value of lambda lies between 4 and 5. Now, our objective would be to find the suitable value of lambda by considering graphical method. This slide shows that the cost versus lambda graph. From the similar triangle of PNR and RMQ, we can easily find the length of NR, which is equal to 0.8. This indicates that the most suitable value of lambda is 4.8 approximately, corresponding to which the cost of inventory is 999.5, which is sufficiently close to rupees 1000. Therefore, the most suitable value of lambda can be regarded as 4.8. When lambda equal to 4.8, we obtain the required optimal values of the order quantities as q1 star equal to 114, q2 star equal to 105 and q3 star equal to 116 approximately. Now, we consider the model with limitation on inventories. Suppose that the upper limit of average number of all items in the stock is n. Since the average number of item is qi by 2, we have to minimize the average cost c given by c equal to summation over I equal to 1 to up to n half c1i qi plus c3i ri by qi, subject to the condition half sigma I equal to 1 to up to n qi is less than equal to n. Again, if this constraint holds for qi star, then the optimal values of qi star can be accepted. Now, if qi star does not satisfy this constraint, that is half of sigma qi star is greater than n, then the optimum values obtained in equation 3 cannot be regarded as optimal values. So, we apply Lagrange multiplier technique. In this case, the Lagrangian function L is given by L equal to summation I equal to 1 to up to n half c1i qi plus c3i by qi plus lambda into half of sigma qi minus n. From the first order optimality condition, we can find the optimal values of qi as qi star equal to root over 2 c3i ri divided by c1i plus lambda star, where I varies from 1 to up to n, and sigma qi star equal to twice n. Next, we consider the model with limitation on storage space. This is model 4C. Suppose that in an inventory system, n items are competing for a limited storage space. Let capital A be the maximum storage area available for n items, and Ai is the storage area required per unit of the ith item. Qi is the order size of the ith item. Then the storage requirement constant is given by sigma Ai Qi is less than equal to A. The Lagrange multiplier method yields the general solution of this problem. However, before applying this method, it is necessary to check whether the unconstrained value of Qi given by equation 3 satisfies the storage constraint. If not, then as in the previous cases, the new optimal values of Qi can be determined by satisfying the storage constraint in equality sense. In this case, the Lagrangian function can be defined as L equal to summation I equal to n half C1i Qi plus C3i by Qi plus lambda into sigma Ai Qi minus A, and then from the first order conditions we can find the value of Qi star as root over 2 C3i Ri by C1i plus 2 lambda star Ai, and that value of Qi star should satisfy the equation given in equation 12. Now, let us consider an example. A small shop produces 3 machine parts 1, parts 2 and parts 3 in lots. The shop has only 650 square feet of storage space. The data for 3 items are given in the following table. So, for the 3 items, demand rates are 5,000, 2,000 and 10,000 respectively. Procurement costs are 100, 200 and 75 respectively. Cost per unit are 10, 15 and 5 respectively, and floor space required are 0.7, 0.8 and 0.4 square feet per unit respectively. The shop uses an inventory carrying charge of 20% of average inventory valuation per year. If no stock out is allowed, we have to determine the optimal lot size for each item under the given storage constraint. Then using the equation 11, we can obtain for lambda equal to 5, Q1 star equal to 333 units, Q2 star equal to 270 units and Q3 star equal to 548 units. The storage space required then is equal to summation Ai Qi star, where summation varies from I equal to 1 to up to 3. Then this sum is equal to 668.3, which is more than 650 square feet, that is the available storage space. Now, for lambda equal to 6, we compute Q1 star equal to 310 units, Q2 star equal to 252 units and Q3 star equal to 509 units, and then the corresponding total storage space equal to 622.2 square feet, which is less than 650 available storage space. Then plotting these results in the graph, we find the most suitable value lambda as 5.4. The lot sizes then are Q1 star equal to 324 units, Q2 star equal to 263 units and Q3 star equal to 511 units. The total storage space required is 649.6 square feet, which is very close to the available storage space 650 square feet. So far, we have developed multi-item inventory models with limitations. Limitation on investment, limitation on inventories and limitation on warehouse storage space. We have seen that if some constraints are there, then we can use Lagrange multiplier technique, provided that the optimal solution should have some effect on the constraint. And also we have seen that if when we consider Lagrange multiplier technique and the constraints has some effect on the optimal solutions, the constraints are all binding, that is, the constraints must hold in equality sense. Let us now proceed to develop another model, that is model 5, which is purchase inventory model. Suppose that the demand rate R is constant and shortages are not allowed. The purchase cost per unit item is P and the cycle length is T. Let I be the cost of carrying 1 rupee in inventory value for 1 year. Since the lot size is Q equal to RT, therefore, the inventory holding area can be easily obtained as half Q into T. that is equal to Q square by 2 R. If we think of inventory holding cost in terms of inventory value, then Q square by 2 R can be expressed as Q by 2 R into Q. This means that Q quantity should be purchased Q by 2 R times. Hence, the holding cost can be obtained as the ordering cost part of the inventory value plus purchase cost part inventory value. So, since for one lot size Q we need C3 as the ordering cost and QP as the purchase cost, therefore, the total holding cost would be C3 plus QP whole into Q by twice R into I. Therefore, the total cost for period T is C3 which is ordering cost, QP which is purchase cost, and then the next two terms are for holding cost. Hence, the total cost per unit time can be written as CQ equal to C3R by Q plus PR plus C3I by 2 plus QPI by 2. Here the term C3I by 2 being constant throughout the model may be neglected for the purpose of minimization or comparison of total cost. Therefore, we can consider CQ as CQ equal to C3R by Q plus PR plus QPI by 2. From the first order necessary conditions, we get dC dQ equal to 0, which gives Q star equal to root over 2 C3 R by Pi. Substituting the value of Q star in equation 13, we get the optimal total cost per unit time as CQ star equal to root over 2 C3 R Pi plus PR. Now, we consider inventory models with price breaks. First, we consider model with one price break. When there is only one price break, that is one quantity discount, the situation may be stated as follows. The range of quantity is 0 less than equal to Q1 less than B, then the purchase cost is P1, and when the quantity is greater or equal to B, then the purchase cost is P2. Here B is the quantity at and beyond which the quantity discount applies, and obviously P2 is less than P1. That means, when we purchase more quantities, we have purchase cost is less. Now, in order to solve the model, we can follow some steps. In step 1, we first compute Q2 star by using the formula 14. If Q2 star is greater than equal to B, then we get the optimal solution, optimal lot size is Q2 star. Now, if Q2 star is less than B, then the quantity discount no longer applies to the purchase quantity Q2 star. Furthermore, the minimum cost occurs at a point for which Q2 star is less than B. So, the average total cost will be monotonically increasing over the entire price range, that is Q2 is greater than equal to B, and the minimum cost for range Q2 greater than equal to B will occur at Q equal to B. Hence, to determine the optimal purchase quantity, we only need to compare the average total cost for lot size Q equal to Q1 star with that for lot size Q equal to B. From equation 13, we find that C Q1 star equal to C3R by Q1 star plus P1I Q1 star by 2 plus P1R, and similarly we can get CV equal to C3R by B plus P2IB by 2 plus P2R. Now, if we compare equation 6 and 7, then we find that C3R by B plus P2R is less than C3R by Q1 star plus P1R. since Q1 star is less than B and P2 is less than P1. But the term half P2 into IB may or may not be less than the corresponding term half P1 I Q1 star. However, if C Q1 star is less than C B, then we can say that Q1 star is the optimum order quantity, otherwise B is the optimum order quantity. Let us take an example and see how this algorithm works. Find the optimal order quantity for a product for which the price breaks are as follows. When the quantity varies from 0 to 500, the unit cost is 10. When the order quantity is greater than or equal to 500, the unit cost is 9.25. The monthly demand for the product is 200 units. The cost of storage is 2% of unit cost and the cost of ordering is rupees 100. In this case, we have R equal to 200 units per month, I equal to rupees 0.02, C3 the ordering cost equal to rupees 100, and P1 equal to rupees 10 and P2 equal to rupees 9.25. Therefore, using the formula for purchase quantity, the basic formula, we find that Q2 star equal to 465 units, which is less than B1 equal to 500. So, Q2 star is not the optimal purchase quantity. Now, we proceed to find Q1 star. Again, for this we use the basic purchase quantity formula, Q1 star equal to root over 2 C3R by P1I, which is equal to 447 units. We now compute C Q1 star and CV, that is C 447 and C 500, and from this we see that the CB is less than C Q1 star. Therefore, the optimal purchase quantity should be Q star equal to B equal to 500 units. Now, we proceed to the model with two price breaks. Two price break situation may be represented as follows. When 0 less than equal to Q1 less than B1, the purchase cost is P1. When B1 is less than equal to Q2 less than equal to B2, the purchase cost per unit is P2. And when Q3 is greater than equal to B2, the purchase cost is P3. Here B1 and B2 are the quantities which determine the price breaks, and obviously we have P1 greater than P2 greater than P3, that is P3 is the minimum purchase cost per unit. For this model, we may follow the algorithm as given in the slide. In the first step, we compute Q3 star, and if Q3 star is greater than equal to B2, then the optimum quantity should be Q3 star, otherwise we have to proceed to next step. In step 2, we compute Q2 star. Since Q3 star is less than B2 and Q2 star is also less than B2, there are only two possible cases, either Q2 star is greater than equal to B1 or Q2 star is less than B1. Now, if Q2 star is less than B2 and Q2 star is greater than equal to B1, then proceed as in the case of one price break only, that is compare the cost C Q2 star and C B2 to obtain the optimum price quantity, purchase quantity. The quantity with lower cost will give the optimum solution. Now, if Q2 star is less than B1 and B2 both, then we proceed to next step. In step 3, we compute Q1 star, which will satisfy the inequality Q1 star is less than B1. Then we compare the average total cost C Q1 star with both C B1 and C B2 to determine the optimum purchase quantity. In this model, we have developed multi-item inventory models with limitations. We have also studied purchase inventory model, and we have used the optimal results of purchase inventory model to find the solution of inventory models with price break. Here we consider inventory model with 1 price break and 2 price breaks, and we have also given some examples to demonstrate the developed models.